This is Chapter 6, Part 1, Applications of Newton's Laws. We're going to learn about things like friction and pulleys and the distribution of forces and something else called static equilibrium. And all of these concepts are important for mechanics, for building, for construction, and for many useful things. So hopefully you'll like this section, although it is kind of challenging. It does have some fairly intense problems, but the concepts are interesting.
Now, the first thing we'll talk about is coupled motions. So when forces are exerted on connected objects, their accelerations are the same. And that's kind of, if you think about it, it makes sense because the string between them is what connects them. And so it's almost like you have one single object. It's just that you have a string between them. And so if one object accelerates, well, obviously the other one will as well at the same rate. So if there are two objects connected by a string and we know the force and the masses, we can find the acceleration and the tension. All right, so if you look at this diagram here, we see we have masses m1 and m2. They're connected by a string in the middle. Now notice that that tension goes both ways, and T is simply a force, and the T stands for tension. This part of the string, we can see the tension is a force that's being exerted to the right on m2, but that same tension is also a force that's being exerted to the left on mass m1. Now, the source of this tension in the middle is the tension of the string on the right, and the person supplying that force is pulling to the right, and that's why I have here F, for that applied force, equals T, because it's the same magnitude. Now, what happens is we're going to have a net force on these two connected masses, and that will produce an acceleration, and that's this vector indicated with A. And as you remember from the last section, F equals ma by Newton's second law. All right, so the first kind of coupled motion we'll study is this situation where you have a mass on a frictionless table, and we can simulate that, of course, in class with the air track, as I explained earlier. But so for this particular diagram, you have to keep in mind that the surface here is frictionless, and then we have it being pulled to the right, and is pulled to the right because there is a falling weight m2 on the right hand side. Now notice what's happening. Let's look and understand these vectors first. Okay, so this one here, Fw1, just means the force of weight for mass 1. And that, of course, as you know by now, is just equivalent to m1g. Now we also have this normal force, and that would be the force of the surface pushing up on m1, since they're equal and opposite. Over here to the right, we have Fw2. That's the second force of weight of mass 2, and that's also mg. It would be m2g. Notice that this vector Fw2 is greater in magnitude than this vector t. Okay, so as you probably have figured out by now, this m2 is going to fall, but it won't fall as fast. It won't fall as fast as if it hadn't been attached to a string, because this tension here is slowing down the fall of m2. Now this is the same principle that's used in elevators because we have counterweights that slow your fall if you descend in floors. And the reason it works is because this tension here, as you can see, is opposing the motion of m2. Now this falling mass m2, although it won't fall as fast, is still going to produce an acceleration. And that's because we have a net force. See how Fw2 is greater in magnitude than t? Well, that's going to give us a net force downward on m2. And that acceleration downward of m2 is equivalent to an acceleration towards the right of m1. Okay, so just take a moment to study and understand the picture and, get a feel for all the vectors. And we will be doing a lot of problems like this. You'll see many situations like this throughout the year. So it's good to take the time to just kind of look it over first and understand it before you go on. All right, let's suppose that if we knew that m2 was 50 kilograms, 50.0 kilograms, and M1 was 100.0 kilograms. What is the acceleration? What is the tension? Now, obviously this is your first time doing this kind of problem, so I wouldn't expect you to do this on your own. Just follow the walkthrough of the solution, and then you'll have a chance to do a different one on your own. Okay, so we're given the mass m2 and we're given the mass m1. And we're asked, what is the acceleration? What is the tension? Well, one thing we know before we even get started is that this acceleration up here at the top of the screen, that purple vector, is going to be equal in magnitude to this acceleration here, the purple vector on the bottom right. Now, the only difference between those two vectors is the direction, but the magnitude is the same. So if we find 1A, we found them all. Think of it that way. Also, what is the tension? Well, notice that the tension here that is pulling to the right on M1 is equal in magnitude to the tension here that's pulling up on M2. So if we found one tension, we found them all. All right, so that makes the problem simpler. Now, to start with a solution, we just label our masses. We have 100.0 kilograms and we have 50.0 kilograms. And we write T equals M1A, and so that's 100.0A. Now, why is that true? Think of it as the same as F equals MA. It's just that we're replacing F with T here because T is a force. And so we have T equals M1A, and we know M1 is 100.0, and we're trying to find A. We also have FW2 equals M2G. That's the force of weight. Now we know that M2 is 50.0, and so we can multiply that by 9.81 to figure out the magnitude of FW2, which will be 490.5 newtons. Now 490.5 minus T equals the net force on M2. Let's take a moment to understand that. Look at M2 here on the right. We can see there's a downward force, FW2, which we found to be 490.5. But that downward force is being opposed by the force of tension, and that's why we do 490.5 minus T. That would be the net force on M2. We have F equals M2A from Newton's second law. Remember that the sigma is just a symbol for sum of forces, or net forces. Net force would be what you get when you take into account every other force. And so we have 490.5 minus T equals 50.0A. Now the reason that these two equations are highlighted in blue, we see one up here, we see another one down there, is because those are our two main equations. We'll be using those for the rest of the solution. But make sure you understand here why they're true based on Newton's second law and on the fact that one force is opposing another. Okay, going on with the solution, I bring those two blue equations forward, and I bring them forward because we're going to be using them using the method of substitution with these equations. So the first step then is, since we know that T equals 100.0A, we put that in for T, and we now have the equation 490.5 minus 100.0A equals 50.0A. Continuing on doing the steps of algebra on that equation, we have 490.5 equals 150.0A, and then we can finally come up with 3.27 meters per second squared as the value of A, the acceleration. Keep in mind that that is the downward acceleration of M2, but it's also the rightward acceleration of M1. Just quickly going back to the diagram, you can see that M2 goes down, M1 goes right. Okay, so we have 3.27 meters per second squared. And now we can use the fact that T equals 100.0A because we want to find out what the tension is. And so we just plug in the value and we end up with a tension of 327 newtons. All right, now this is a problem that you can do on your own. If in the block and pulley system below, M2 is 120 kilograms and M1 is 95.0 kilograms. Neglecting friction, how long will it take M2 to fall a distance of 2.5 feet? All right, so the problem isn't exactly like the last one, but it's pretty similar. And if you keep in mind some of your Chapter 3 equations, you should be able to get the answer. Okay, now I did get you started with the sketch here, so let's take a moment to look at the sketch. We've got M1 being accelerated to the right because of tension T. We have M2 being accelerated down because of FW2 minus T. We also have acceleration here, downward for M2 and to the right for M1. And notice how the displacement is labeled. 2.5 feet is how far it falls vertically, and that's why we have it listed as S sub y. All right, so pause the video now, take time to do this on your own, and then resume when you get your answer or if you get stuck. All right, so the first equation we can come up with is T equals M1A, and that would be 95.0A. We just plug in the value of M1. We also know that FW2 equals M2G, and so that's 120 times 9.81, which is 1,177.2 newtons. Now we are going to have a net force on M2, and so it's 1177.2 minus T, since the T opposes the force of weight. And that gives us, using F equals ma, 1177.2 minus T equals 120A. Now we have those two equations marked in blue because we're going to be using them for the rest of the solution. T equals 95.0A, 1177.2 minus T equals 120A. So now we're going to solve by substitution. We plug in our 95.0A, and we are able to solve for A and find that it's 5.47535 meters per second squared. Remember, we don't round until the end, and that's why we are keeping it with all those decimal places for now. Now, our vertical displacement, if you convert it to meters, is 0.762 meters. And so we have our S sub y of 0.762, and the best equation for us to use is S sub y equals VIYT plus 1/2 AT squared. Okay, now that we have that equation, the rest is just plugging and chugging. And so you can plug in what you know, chug through the calculation, and when you solve for T, you'll find that T equals 0.53 seconds. Now that is the final answer, and so that we do need to write with the appropriate number of significant digits, and that's 2 for this problem. All right, so the next thing we're going to talk about is friction. Friction is caused by surfaces that are not completely smooth. Notice here we have a wooden crate on a floor, and if you look at this little square is being magnified so that we are kind of zooming in as if we were looking at it under a microscope. Notice how even though the bottom of the wooden crate to the naked eye looks straight, it's actually not straight. It has all kinds of jagged edges in it, and the floor also has all kinds of jagged edges in it. And so when these two surfaces are in contact with each other, there's going to be friction because they are not smooth. This is the source of friction. It's the interaction of surfaces and the different contours of surfaces. And as you know from your experience, some things have more friction than others. For example, if you rub your finger on a piece of ice, there's going to be a lot less friction than if you rub your finger on a piece of rubber. Okay, if you wear shoes that are rubber shoes, well, you're going to get more friction on the road, which is better for you, than if you wear shoes that have, glass soles. Now, most people don't have glass slippers. Cinderella did, But you know, if you walk around in a glass slipper, you're going to be slipping all over the place because glass is a smoother surface than rubber. All right, now these interactions of surfaces, which we call friction, they really depend on each surface, as we're going to find out in a little bit. First, static friction. There are two kinds of friction we'll learn, static and kinetic. We're going to talk about static first. This is the friction experienced by resting surfaces in contact with another. Okay, so going back to this image, if this wooden crate is just standing still, that's called static friction. Now, the static frictional force depends on the normal force, and this is the relationship. FSF equals mu s Fn. Now, what does all this mean? Well, FSF just stands for the force of static friction. Mu sub s is the coefficient of static friction. This is always a given. It's a constant, and you can solve for it if you're given other things, but the mu is a constant that depends on the materials. So don't worry about where it comes from yet. And F sub n is the normal force. This is the force that pushes up on the surface. Now, to make sense of this, think of it this way. All right, if you take your rubber shoe and you take it off your foot and you try to slide it on the floor, well, it's going to slide pretty easily. But if you put that shoe on and you stand in it and then someone else tries to push it along the floor, much harder. Why is it much harder? Because you have more weight going down, which means there's also more normal force going up. Okay, so it stands to reason, if you think about it, that the force of friction depends on the normal force. A heavier object will have more friction than a lighter object. Why? Because it's pressing down harder on the surface and causing more friction, more resistance to motion. The constant mu sub s is called the coefficient of static friction. It is specific to both surfaces. So, for example, if you have an ice cube on a hockey rink, that's going to have 1 mu s, which will be very low. But if you have a rubber eraser on a wooden ramp, well, that's going to be a different coefficient of static friction, much higher, as you can imagine. All right, so it's material dependent. It depends on both surfaces, not just one surface, but both surfaces. The static frictional force is independent of the area of contact between the surfaces. Now, this is something that surprises a lot of people at first, because we tend to think of something with a lot of area as having more friction than something with a little bit of area. And that's kind of intuitive because, you know, if friction is between surfaces, and if there's more surface area, you would think there's more friction. Well, there's a reason why this is not true. Okay, if the surface area is small, you've got more pressure, and so if more pressure means more force is concentrated on a small area, and that higher degree or higher value of normal force will give you more friction. However, if you have a bigger area, well, that normal force is being spread out. It's being spread out, and so it's diluting, if you will, that force of friction. Now, the bottom line, you don't have to think about the reason for it all the time. The bottom line is that static frictional force is independent of the area of contact. And you can do an experiment like that if you want. You could put your book flat on the table and try to push it. And then you could put your book, the same book, sideways on the table, on the binding, try to push it. You'll notice that it requires the same amount of force to push it either way, even though in the flat book scenario you've got more area, and in the book on binding scenario you have less area. Kinetic friction. This is the friction experienced by surfaces sliding against one another. The kinetic frictional force depends on the normal force. Now, let's back up just a little bit. If we have static friction, that means that the objects are not moving. With kinetic friction, the objects are moving. They're actually sliding against one another. As we're going to see, kinetic friction is actually less than static friction. And when you think about it, it's because there's less interaction between surfaces that are moving against each other than there is between surfaces that are not moving or are resting against each other, because the molecules of the surface have less time or less opportunity to interact. Now, the relationship is the same for frictional force as it is for the static frictional force if we compare it to the kinetic frictional force. It's really a similar relationship, and that is that it depends on a coefficient mu. So this equation is FKF equals mu k Fn. And all that means is that the force of kinetic friction equals the coefficient of kinetic friction multiplied by the normal force. The constant mu k is called the coefficient of kinetic friction. It also is specific to both surfaces. All right, so just as for static friction, it depends on each surface. The same is true of kinetic friction. And as for the static frictional force, the kinetic frictional force is independent of the area of contact between the surfaces. Let's take a look at this diagram to help us understand static friction and kinetic friction. So here we have a block resting on a surface, and it's at rest, so the V is 0. And it also has a force of 0 static friction because there is nothing that is causing or trying to make this object move, and therefore there is no friction opposing any motion. It's just staying still. Now, what happens if we try to move the object? Well, over here we have a spring scale, and we're pulling it to the right. But notice that we have an equal and opposite vector on the left, which is called negative f sub 1, because it's equal and opposite to f sub 1. And that negative f sub 1 is completely equivalent to the force of static friction. The force of static friction is opposing with an equal and opposite force the force that my hand is exercising by trying to move this block to the right. Now notice here in the third frame we have the same kind of thing, but the force of friction has gone up. Why? Well, because the applied force of the hand has gone up. Now, you can do this experiment again with your book on the table. If you try to push the book, well, you can try to give it a very tiny force, it's not going to move. Then try to give it slightly more force, it's still not going to move. Even more force, it's still not going to move, until you reach a certain critical force, which will overcome friction and make the book move. Okay, that's what we see here in the diagram. We see how friction can oppose an applied force, and that friction force is variable depending on the applied force until the applied force exceeds that critical threshold, and at that point we're going to have a velocity and we're going to have motion. Now notice at this bottom frame we still are having friction oppose the motion, but now it's kinetic friction, not static friction. Notice also that the kinetic friction is less than the static friction, and that's because since the surfaces are moving in contact with each other, those surfaces have less opportunity to interact, and therefore there's less friction. Now, the static frictional force keeps an object from starting to move when a force is applied. The static frictional force has a maximum value, but may take on any value from 0 to the maximum. So if we look at these middle two frames, well, this F1 force is definitely between 0 and the maximum because the thing is it's not moving yet. And this F2 force is definitely between 0 and the maximum. Right here we have negative F1 and then we have negative F2. That's between 0 and the maximum. But it hasn't reached or exceeded that maximum yet because it's still motionless and it's not moving. This is an animation to help us understand friction, and what I like about it is that all the vectors are labeled so we can really learn how friction works. Okay, we have a heavy wooden crate. The robot is trying to push it horizontally. In order to do that, it has to overcome the force of friction. All right, so we have a mass of 100 kilograms. We're using a g of 9.8 meters per second squared. We have a coefficient of static friction, mu(s), of 0.5, and a coefficient of kinetic friction, mu(k), of 0.3. All right, let's see what happens if the robot applies a horizontal force of 100 newtons. Well, look at that. It's pushing. We see this Fa, or applied force vector, but equal and opposite to it is the force of friction vector. In other words, this force is still not enough to overcome the friction. All right, what's going to happen if we increase to 200? Well, the applied force doubled, but so did the force of friction. All right, how about 300? Well, we got more applied force, but the force of friction also went up. All right, what if we put it at 400? Still not enough. All right, how about 490? Still not enough. All right, well, let's try to understand what's going on here. We've got friction holding us back, but notice how the friction kept reacting to the applied force to become equal and opposite to it. Well, let's look at this number, 490. All right, the mass is 100, g is 9.8. 100 times 9.8 is 980 newtons. But if you look at your static friction equation, the force of static friction equals mu(s) times Fn, and mu(s) is 0.5. So 0.5 times 980 is 490, and that is the applied force. What that means is this is the absolute maximum force that the robot can exert on the crate and still not move it. Okay, now let's look at what happens if I increase this to 491. Okay, so watch the crate, and here we go. Look at that. It started to move. Why? Because it was able to overcome the force of static friction. Now notice something very important here. The crate has overcome static friction. It's still being held back, or at least the acceleration is being slowed by the force of friction vector. But notice that this force of friction vector is much smaller. And that's precisely because since the thing is moving already, we've paused it here, right? But it was moving when I paused it. Well, that force of friction is the force of kinetic friction, which is always lower than the force of static friction because the surfaces don't have as much opportunity to interact with each other. Okay, now there's something neat we can do here. If we reset these, notice what's going to happen here. I'm going to put it back to 490, okay, and see how big this is. All right, do you see how big that FF is? Now, watch what happens when I increase it to 491, and I want you to keep your eye on this FF vector. Right now it's very large because that's all static friction and nothing has moved yet. But notice when it starts to move with that 491 newtons, look at what happens to the FF vector. Keep your eyes on it. Here we go. Did you see that? Did you see how it suddenly shrank? The very instant that the crate gets moving, suddenly the friction force goes way down because now we're dealing with kinetic friction rather than static friction. Okay, so this has just been to demonstrate a little bit about friction. Now let's see what happens if we cut this down. Remember, he's been moving, and so we can get by with a lot less force to keep it moving. You need a lot of force to get it started moving, but once it's moving, you need much less to keep it moving. Let's try 300. Will it still move? Yes, it's still moving. Let's try 250. Will it still move? Yes, it's still moving. Let's try 200. Will it still move? Yes. Let's try 50. Will it still move? Yes, but look at what happened. It did keep moving for a little bit, but eventually the force of kinetic friction slowed the motion so much that it came to a stop. All right, so here we have a chart of typical coefficients of friction. And as I said earlier, these are dependent on the surfaces. So for example, rubber on concrete, that has a very high, as you could probably guess, coefficient of friction, 0.8 for kinetic and between 1 to 4 for static. Steel on steel, as you could also guess, is less than that. These are smoother surfaces. And glass on glass is even less because glass is even smoother. And so we have the different combinations here: wood on leather, copper on steel, rubber on concrete, steel on ice, waxed ski on snow. Look at how low that one is. Waxed ski on snow, 0.05. And that's precisely why if you wax your ski and ski down the mountain, you're going to go very fast because there's little friction. All right, and if you look at the synovial joints in humans, wow, that's tiny, 0.003. And that's why we're able to move our joints and move our limbs all over so freely, because there's very little friction in our joints. Okay, here's your first friction problem. If you use a horizontal force of 30.0 newtons to slide a 12.0 kilogram wooden crate across a floor at a constant velocity, what is the coefficient of kinetic friction between the crate and the floor? Alright, so since this is your first one, you probably want to see at least the first few steps of the solution. Then you can probably do the rest on your own. So we'll get you started with a sketch. Here we have the wooden crate and it's resting on the floor. And we can sketch our givens. We know that there is a horizontal force. Now, the problem does not state whether that goes to the right or left, and so you can choose in that situation. If you like right, go right. If you like left, go left. Okay, here we have one to the right. That's a force of 30.0 newtons. And then we have the force of kinetic friction opposing it, 30.0 newtons. Now you might wonder, well, why is it exactly the same? That's because the problem tells us that it's moving at constant velocity. And as you know from Newton's second law, and also from the first law, with constant velocity, there is no force. Things tend to stay at constant velocity, or they tend to stay at rest, unless there's an applied force that causes them to move. Now, here we have an applied force, but it's being opposed by an equal and opposite force of friction. So we can get this thing to move, but since there's no net force, you can see 30 equals 30, there will be no acceleration. F equals ma, there's no force, therefore there will be no acceleration. Alright, now we have our normal force, F sub n equals Fw, and we know that Fw is mg. So this would be the free body diagram for the problem. You can see all the force vectors, and we have the velocity vector. We don't care what the velocity is. All that we need to know is that it's constant, because whether it's a small velocity or a big one, if it's constant, that means that there is no net force, and therefore no acceleration. Okay, at this point, you might want to try the rest on your own if you feel confident. If not, just watch the rest of the walkthrough, and then you'll have a chance to do one on your own. Alright, so here's the solution. We have FKF equals 30.0 newtons, that's a given. We have F sub n equals F sub W equals mg. That we can calculate because we know that the mass is 12.0 and g is 9.81. So we have 117.72 newtons. And notice that we can see all that here in the givens and in the drawing. Okay, going back, we have mu sub k, which is question mark. That's what we're trying to find, the coefficient of kinetic friction. We use our kinetic friction equation, and so FKF equals mu k Fn. We rearrange that to isolate mu k, and then we do our plugging and chugging step and end up with 0.255 as our coefficient of kinetic friction. Here's another problem. This one you can definitely try on your own. You should try on your own. An eastward force of 40.0 newtons accelerates a 5.0 kilogram block at 6.0 meters per second squared along a horizontal surface. How large is the frictional force? All right, so remember the three main steps. You need to sketch, you need to do your layout, and then you need to identify your equation. Pause the video, try this on your own, and then resume when you have your answer or if you get stuck. Okay, so here's the free body diagram. We have our force vectors labeled, and we also have an acceleration vector here that's given. That's going to be 6.0 meters per second squared. We have our applied force of 40.0 newtons. Now, we know that that's going to be more than the force of friction because it's accelerating. And we have our weight vector, and we have our normal force vector. Proceeding then with the layout, we know the applied force is 40.0 newtons, mass is 5.0 kilograms, acceleration is 6.0 meters per second squared, and we write a question mark for FKF. Third step, we identified the equation, and first we know that F net equals F minus KF. Now the reason we know that, that's not from some formula, that's just from understanding what the net force is. Let's go back to the diagram. Well, we know that this red vector here, F, must be greater in magnitude than the blue vector of friction. And that's because it's causing acceleration. And we know from Newton's second law that only a net force will cause an acceleration. And so if we're looking for that net force, we know that it's F, which is bigger, minus FKF, which is smaller. Now we also know from Newton's second law that F net equals ma. Now rearranging these equations, we have F minus FKF equals ma. And then we can do our plugging and chugging. And so now we just put in what we know and find what we don't know. And FKF equals 10 newtons. All right, here's another problem. You are driving a 2,500 kilogram car at a constant speed of 14.0 meters per second along a wet level road. As you approach an intersection, the traffic light turns red. You slam on the brakes. The car screeches to a halt in a distance of 25.0 meters. What is the coefficient of kinetic friction between your tires and the wet road? All right, what I suggest for this one, since it's a little more complicated, is you probably want to see the sketch, and then you can do the rest on your own. If you really want a challenge, you could try doing this completely on your own. That's fine too. But just remember that the more you try on your own, the better you learn. But whenever you get stuck, or if you want to check your answer, you can watch the rest of the solution. Okay, so starting with the sketch, we have two frames here. On the left, we have it just at the moment where he starts or slams on the brakes. And then on the right, we have that moment where it's come to a complete stop. The car has completely stopped. Now, looking here on the left, we have our force vectors. The force of weight going down, the normal force going up. That, of course, is equal and opposite to the force of weight. We have the kinetic friction, and that would be the force that is exerted on the tires and on the road, which would try to slow the car down once the tires lock up. We have acceleration going back. Why is it going back? Well, because even though the car is going forward, the acceleration is trying to slow the car down. So that would be a negative acceleration. Another word for that is deceleration. But that's why the red vector A is going opposite to the car's motion. We have the mass of the car labeled, 2,500 kilograms. And then over here on the right, we have, of course, the same mass, same FW, same FN. But now we have this little green vector, which, as you know, is just zero magnitude. But we're putting that little arrow as a placeholder, as a marker, just to kind of keep it straight in our heads. And then we have this displacement, this horizontal displacement of 25.0 meters, which was given to us. And that tells us that the car goes from 14 meters per second to 0 in 25 meters. That's the stopping distance. how far it takes, or how far it goes until it comes to a complete stop. Okay, our layout, we have, we write our givens, so we know that Fn equals Fw, and that's mg. We calculate that to 24,525 newtons. We know that S is 25.0 meters. We know that m is 2,500 kilograms. Vi is 14.0 meters per second. Vf is 0 meters per second. We need to find A, and we need to find mu k. Okay, so the challenge when you have a layout like this where there are a lot of things you know and a couple of things you don't, is you have to figure out, well, what am I going to try to find first? Now, since we're given the details of this trip, if we want to call it that, this deceleration trip, it's convenient to try to find A first. And so we're going to use Vf squared equals Vi squared plus 2As. Doing our plugging and chugging, we end up with an A that we can calculate to be negative 3.92 meters per second squared. Now that we have the A, we can try to figure out mu k. And for that, we'll need to find the force of friction. So we have FKF equals MA. We know that because the magnitude of FKF, that frictional force, is causing the deceleration, which is just the negative acceleration. And so we have FKF equals 2,500 times negative 3.92, and that gives us negative 9,800 newtons. All the negative means is that it's opposing the motion. Now, using our friction formula, FKF equals mu k Fn, we end up with 9,800 equals mu k times 24,525. Now, by convention, remember that certain things in language or in science or in math are really just human conventions. They're symbols that were chosen, ways of doing things. And so one of those conventions is that mu is always positive. All right, so since we're looking for mu and we know that it's always positive, that's why we use the absolute value of this force. And we end up with mu k equals 0.400. Okay, now we're going to look at inclined planes. You've been introduced to these already, but let's take a closer look at them. So an inclined plane is basically just a ramp. And here we have an object, this green box, sitting on the ramp, and it's sitting still. It's being held back by the force of static friction indicated by this orange vector. Now, let's look at these other vectors. We have the force of weight, which is going straight down into the earth. That equals mg. And then we resolve the force of weight into its components. One component is parallel to the ramp surface, FWP, and the other component is normal or perpendicular to the ramp surface, and that's FWN. We have FWP as FW sine theta, and FWN is FW cos theta, and this theta equals the theta of the ramp itself. Quick little proof on that. What we can do is we can look at this as a right triangle, and we can also look at this as a right triangle. And now, if we have theta, well then this angle here must be 90 minus theta. It's a little bit hard to write with the pen, but you get the point. You have to use the trackpad to do this. 90 degrees minus theta. And if that's 90 degrees minus theta, well then this must be theta. All right? And what that means is that this little triangle is similar to the big triangle of the ramp. All right, so we have our theta, and the last vector to explain is this f sub n, which is equal in magnitude to fwn. Now I'm just going through this so that we can look, have a clean look at the ramp. All right, so it's equal in magnitude to fwn, and we can see that the purple vector is exactly the same length as the red vector. All right, one last little thing to explain is that you could have drawn this differently, and it's just as good. You could have drawn this like this. All right, I'm going to just kind of draw. It's not a good drawing, but just you get the point. um, I'm drawing this guy down here, and then over, it's going to go over this way, right? And what you can see is that this acute angle is going to be theta. Why? Because this line straight down here is just the FWN vector that's been moved, and this line down here is just the FWP vector that's been drawn elsewhere. And notice that it's still going to be the same theta. So you can draw it that way if you want. Just make sure that you always draw things the same way so that you don't get confused. All right, so the inclined plane is basically a tool that can be used to lift things. It makes it easier to ascend a height. Here's our first inclined plane problem. A 15.0 kilogram steel toolbox is resting on an adjustable steel ramp. The coefficient of static friction of steel on steel is 0.740. At what ramp angle will the toolbox begin to slide? Okay, so what I'm going to do for you in this problem is I'm going to give you the sketch, and then at that point I'll ask you to do the rest on your own. So here's the sketch. Let's make sure we understand it first. All right, we have the same box on a ramp, and this is an adjustable ramp, which means that the angle can be increased or decreased. If the ramp is on hinges, that's possible. I have my force of static friction vector, which equals mu s Fn by definition. That's the definition of static friction, which we learned today. I have Fw equaling mg, and since m is 15.0 and g is 9.81, I have 147.15. And then I can resolve that into its components. So I have 147.15 sine theta and 147.15 cos theta. And what I'd like to find here is after which angle or beyond which angle will this green box begin to slide. In other words, beyond which angle will it completely overcome the force of static friction. All right, now in every situation, depending on the box's normal force and also the coefficient of friction, there's always going to be a maximum angle. And so what this problem is asking you for is at what ramp angle will the toolbox begin to slide? And so what you're going to have to do is you're going to have to think of things in terms of theta and put things in terms of theta in order to solve. Now, one last thing before you try the rest on your own. Since this is your first inclined plane problem, it's probably good for you to see the layout, and then you can do the rest. All right, so here's the layout. I know that mu s is 0.740. I know that Fn equals Fwn equals 147.15 cosine theta newtons. I know that Fwp is 147.15 sine theta newtons. And Fsf equals mu s Fn newtons. Theta is the question mark. All right, so now, based on what you've learned so far, and based on what you know about static friction, you should be able to do the rest on your own. This solution will involve some trig, so some of you who haven't had trig yet might get stuck at a certain point, but everyone else who has already had trig should be able to finish the problem on your own. Okay, so pause the video, do that, and then resume when you have your answer or if you get stuck. All right, so the toolbox will begin to slide when FWP is greater than FSF. Let's quickly go back to the sketch and understand why that's true. All right, if the blue vector is FWP, it's equal and opposite to the orange vector FSF. Well, obviously, if the blue vector reaches a point where it exceeds FSF, then the green box will move. And that's exactly what I mean here when I say the toolbox will begin to slide when FWP is greater than FSF. And so FWP is greater than mu s Fn, since that is FSF by definition. 147.15 sine theta is greater than 0.740 times 147.15 cosine theta. All we're doing is plugging and chugging. And then to simplify, I have 147.15 sine theta over 147.15 cos theta greater than 0.740. And here's where the trig comes in. Okay, so if you've had it, you already know that sine theta over cosine theta is exactly equivalent to tangent theta. if you don't know that already, quick little proof of it, because it's a useful thing to remember, is that if sine theta is opposite over hypotenuse by definition, and if we put sine theta over cos theta, which is adjacent over hypotenuse by definition, well, look at what happens. The h's cancel, and you're left with O over A, or opposite over adjacent, and that's the same as tangent. Okay, so then this is all going to cancel to simply tan theta is greater than 0.740. Theta is greater than inverse tangent 0.740. And finally, you can find that inverse tangent on your calculator. Theta is greater than 36.5 degrees. So once I adjust this ramp so that the angle is greater than 36.5 degrees, that green box is going to slide. Let's talk about something interesting that you may have seen or used before, pulleys. Now, you're familiar with what a pulley is. You know that it helps in lifting things, but maybe you've never really learned how they worked. So let's examine first what we have here on frame 1, and just ignore frame 2 for now. If you're looking at frame 1, we have a 100 Newton weight that we want to lift, and we're lifting at 10 centimeters. We hook it up to a pulley. Notice that we still have to exercise 100 newtons downward to lift this weight up. But it's easier to pull down because you can actually get your body weight into it. And so this is still an aid in work because it's still making our work a little bit easier. All machines do that, and so even though this is a very simple machine, it still counts as a machine because it makes work easier. Now notice that we're lifting at 10 centimeters, and that lift of 10 centimeters corresponds exactly to a displacement of 10 centimeters of the hook. Now let's move on to frame 2 where it gets interesting. In frame 2 we have two pulleys, and so we have this line. It's wrapped around the top pulley, and then it's wrapped around the bottom pulley, and it's anchored. And so we have these two lines here that are sharing the load. And so the load of 100 newtons gets split up into these two lines 50-50. And since the tension is the same throughout, I have to pull down with a force of only 50 newtons now in order to lift the weight. Now I'm going to pull that 50 newtons 20 centimeters. Look at how I'm pulling the 50 newtons 20 centimeters. I'm pulling that hook, and the weight of 100 newtons goes up 10 centimeters. Now later on in chapter 6 we'll learn about the concept of work and how it's really the same amount of work to lift 100 newtons directly 10 centimeters as it is to exercise 50 newtons over 20 centimeters. However, the 50 newtons of work over 20 centimeters feels easier. It's still the same amount of work, but it feels easier, and that's why we use pulleys, because 50 newtons is certainly less than 100. Now, something that causes confusion sometimes in students is they see this and they think, well, but wait, aren't three ropes sharing the load? Well, no. For one thing, if you look at frame 1, we don't have two ropes sharing the load. There's only one. The hook is something that I am doing. All right, the hook connects to me, but there's only one load here and one thing that supports it, which is the line, and that line is anchored to the pulley. Okay, so what you want to count when you're looking at pulleys is the points of anchor. All right, so we have an anchor right there where I'm pointing with the mouse arrow, and we also have an anchor here where I'm pointing with the mouse arrow. All right, so these are 2 points of anchor. My finger on the hook does not count as a point of anchor. And if you like, you could pretend that this yellow hook were kind of sucked back all the way to the top and then got stuck there. Well, you'd have 2 lines, and so it'd be obvious that the 100 newtons is being split into 50 and 50. Okay, so the basic thing to remember is that the only lines you count when you're looking at pulleys are the anchored ones. You do not count the free line. This would be called the free line, which has the hook on it, the free hook on it. Okay, so the neat thing is that pulleys are able to distribute force. Now let's look at these situations 3 and 4. These are even more interesting. In 3 we have 3 pulleys, and we can see that the line is wrapped around the top pulley and then the bottom and then the pulley right under the top one. And so now we have 3 points of anchor, and because we have 3 points of anchor, we also have 3 lines that share the load. And so 100 newtons divided by 3 is 33 and 1/3 newtons. And so it's going to be easier for me because I just need to exercise a downward force of 33 1/3 newtons. That certainly feels a lot easier than 100 newtons. But here's how I pay for it, right? The price for that ease is that I have to exercise that force over 30 centimeters rather than 10 or 20. Okay, so with pulleys, you pay for the ease with a greater length of motion. And finally, in frame 4, I have 4 pulleys, and therefore I have 4 anchor points. And so those 4 anchor points correspond to these 4 lines here, and I can see that the 100 newtons is distributed into 4, so I have 25 each. Now what this 25 means is that there is a tension of 25 newtons over the whole line. Okay, so I'm going to trace that through, starting with this inner yellow hook. I'm tracing around the whole line, and at every point of this line there is a tension of 25 newtons. If you look at any of the other frames, that was true too. Over any point of the line we have identical tension. That's the whole beauty of the pulley system. Now 25 newtons is definitely much easier than 100, but look, here's the price I pay. I have to pull it 40 centimeters to get only 10 centimeters of lift on that 100 Newton weight. All right, the last thing we'll talk about today is static equilibrium. So when the net force on an object is 0 and that object is at rest, it is said to be in static equilibrium. All right, so this first thing I'm going to do, this isn't a problem that you need to work on. This is a problem that I'm going to work through in order to help you learn what static equilibrium is about. Now, just speaking of the concept, without getting into numbers, static equilibrium just means these two weights are hanging and staying still. They're not moving, and one is not going to move. This 6 kilogram weight is not going to move. Everything is just standing still. But when things are standing still, there are forces involved. There isn't motion, but there are forces involved. And so let's look at what those force vectors look like. Okay, so I've got these vectors here. I have FW1 that's going straight down into the ground, magnitude of M1G. I have FW2 straight down, magnitude of M2G. T2 has to be equal and opposite to FW2. T1 equal and opposite to FW1. And I have T2 getting split up into 2 vectors, T1 and T3. You could say that T1 and T3 are sharing the tension of T2, breaking it up. Okay, now static equilibrium means that all the vectors cancel each other out. Okay, so that means that this vector here, FW2, is canceled out by T2, and I don't have to worry about these vectors here because these vectors here are really just stemming off of T2. And so I have a vertical cancellation of vertical vectors here. I also have a cancellation of vertical vectors here. And I have a cancellation of horizontal vectors because this horizontal vector here, which is simply the component, the horizontal component of T1, is equal and opposite to the horizontal component of T3. Now, I'm going to blow up this little triangle, and we're going to see it here to make things a little more clear. I got T1 and T3. I separated them here so we can visualize. T1 has a component that's opposite the angle 30 degrees, T1 sine 30 degrees, and then it has a component that's adjacent to the 30 degrees, which is T1 cos 30 degrees. All right, and then over here, this triangle looks very similar, as you can see. T3 sine 30 and T3 cos 30 um, for tension 3. Now, I split them apart, but these go together, and you can think of it as this dotted vertical vector sharing the vertical load with this dotted vertical vector. And so the vertical portion of T2, which is purely vertical, as you can see, T2 is purely vertical, that gets distributed into T1 cos 30 and T3 cos 30. Now, the horizontal vectors, T1 sine 30 and T3 sine 30, must cancel each other out, because if one were bigger than the other, we would have motion. But since this is standing still, we can't have one bigger than the other, and still they must be equal and opposite. Now we're going to lay out some equations. Now, before I continue to lay out those equations, this is not something you're going to do on your own, but let's suppose that you were asked to find the magnitudes of T1, T2, and T3, and also find the mass m1. Well, here's how you would go about doing that. First, you would write T2 equals m2g, and that equals 6.0 times 9.81, which equals 58.86 newtons. And if you look at the magnitude of m2, that's simply given to you because it's part of the sketch. 9.81 you know, because it's a constant. So we can, right off the bat, calculate T2. Now T1 equals m1g. We don't know m1 yet, but we know that it's, g is 9.81. So we can write it as 9.81 m1. T2, as I've already said, gets split up, right? And so you could say this purely vertical T2 gets split up into the vertical T1 cos 30 degrees and the vertical T3 cos 30 degrees, which share that load vertically. Okay, so this equation then is valid. And then I have T1 sine 30 degrees equals T3 sine 30 degrees. Okay, this one needs some explaining because you look at that and you're like, well, how do you know that? All right, well, we just need to go back to the concept of static equilibrium, which just means that all the forces cancel each other out. Now notice, if we look back at the main diagram, it's clear how the vertical forces cancel each other out. But look, there are only two horizontal forces, which is this component that I'm circling now with a mouse arrow, and this component which I'm circling now with a mouse arrow. And since those are the only two horizontal vectors, they must be equal and opposite, because otherwise we would have some net motion. And since we don't have net motion staying still, they must cancel each other out. And the only way they can cancel each other out is if they're equal and opposite. So that means the magnitude T1 sine 30 degrees equals the magnitude T3 sine 30 degrees. And that means that T1 equals T3 because the sine 30s cancel. Now, we can bring one of these equations down. I'll show you which one. We're going to bring down this equation, the third one, down to here. We're replacing T2 with 58.86. The rest stays the same, as you can see. And then the one little change that we've made here is that we have T1 cos 30 degrees plus T3 cos 30 degrees. Down here, I have it written as T1 cos 30 degrees plus T1 cos 30 degrees. Why? Because T3 equals T1, so I replace T3 with T1. And now I end up with 58.86 equals 2 T1 cosine 30 degrees. Solving for T1, I get 33.98 newtons. So I've already found part of what I was trying to find. Don't round yet. Bringing forward all of these equations, none of this is new. All of these are just brought forward from the last screen. I left off at T1 equals 33.98. And so now what we can do is we can bring down another equation since we still want to find T2 and T3. And so we can bring down this equation. And what this equation will do is this actually going to help us to find M1, since that's one of the things I want to find. And so I have 33.98, which I just found, equals 9.81 M1. And I can solve for M1 which will be 3.46 kilograms. Again, not rounding yet. Now, final answers. T2 equals 59 newtons with the right significant digits. That's 58.86 in two significant digits. T1 equals T3, which I know, and I know T1 is 33.98, so both of those are 34 newtons. And M1 is 3.5 kilograms. All right, now this is a problem you will do on your own. As you can see, it looks very simple, but static equilibrium problems are actually among the most difficult problems in physics. Static equilibrium problems give you respect for what civil engineers do, because civil engineers design bridges and structural engineers design buildings. Well, obviously architects design them, but the ones who make sure that they actually stand are the structural engineers. And so all of that is statics and static equilibrium, figuring out distribution of forces. All right, so you're going to do this on your own, but before you do, I'm going to give you some hints. All right, since you're new at this type of problem. First, I'm going to just help you with a sketch. All right, we have the FW vector. You know that that's going to be mg. And then I also have T2 being resolved into its vertical and horizontal components. So if you just look where I'm circling now with the mouse arrow, I have T2 resolved into its vertical and horizontal components. And now look at this portion, I have T1 resolved into vertical and horizontal components. Now keep in mind as you're doing this problem that when you want to express the components, you're going to be using this angle and this angle. And notice that this angle here is 30. Again, it's very hard to write with this trackpad pen, but at least you can read that. This angle here is going to be 30, but this angle here is going to be 60. All right, because it's the complement. All right, so when you're doing the problem, keep that in mind as you resolve your vectors. Now also the thing to keep in mind is that even though this central dotted vector it looks like just one single vector, we're actually treating it as two because one would be the vertical component of T2 and the other would be the vertical component of T1. All right, now one more thing before you start. Remember that all the forces have to cancel. Okay, so what that means is that this FW is going to be counteracted by the two vertical components. And I'll even circle this. All right, we have a horizontal vector here which must be counteracted by another horizontal vector here in order to have static equilibrium. And that means that they must be equal and opposite in magnitude. Okay, so now pause the video, do the rest on your own, and resume when you have your answer or if you get stuck. All right, the solution. Let's first write down the easy stuff. We know that FW is 2.2 times 9.81, so we have 21.582 newtons. We know that T2 cosine 30 degrees plus T1 cosine 60 degrees equals FW. Why? Let's go back to that. T2 cos 30 means this guy right here that I'm tracing now with the mouse arrow. That's T2 cos 30. And remember, it's like two vectors in one. There's also another vector here, which is T1 cos 60. Those are the two vertical components. Back to the equation, T2 cos 30 plus T1 cos 60 have to add up to FW, since they need to cancel each other out. Now, T2 sine 30 degrees equals T1 sine 60 degrees. Let's go back and explain that. T2 sine 30 degrees is this guy right here that I'm circling now. That's a horizontal vector. But also, T1 sine 60 is this guy over here, T1 sine 60. And since as I said before, they have to be equal and opposite in order to achieve static equilibrium. So we set those equal to each other. And now finally, we can do some rearrangement and calculation. So here's the first thing we're going to do. I know that sine 30 degrees is 1/2. You can prove it to yourself on your calculator. 1/2 T2 equals T1 sine 60. Now I'm going to express T2 in terms of everything else. So I have T2 equals 2 T1 sine 60. Okay, now what I'm going to do is I'm going to bring down, I'm going to bring down this equation here, just this equation here, so that I get 2 T1 sine 60 cos 30 plus T1 cos 60 equals FW. Let's make sure we see where this comes from. Okay, remember, it's just this equation. Notice what I've done. Since I found that T2 is 2 T1 sine 60, well, that has gone here. And so that has replaced the T2 in the top equation. The rest stays the same, cos 30, and then I have T1 cos 60 equals FW. Now we're getting closer to something solvable, aren't we? Now what we're going to do is just some plugging and chugging. We know FW is 21.582. And now we can do some evaluation on our calculator. So we have 1.5 T1 plus 0.5 T1 equals 21.582. Combining like terms, 2T1 equals 21.582, and T1 equals 10.791, or 11 newtons. And therefore, T2, which I already have put in terms of T1, so all I need to do is plug T1 back into that expression. I will have 19 newtons. All right, so static equilibrium problems are actually quite difficult, but the thing to keep in mind is that the vertical forces have to cancel and the horizontal forces have to cancel. When you keep that in mind, these problems actually become easier.
Here's the classwork. Please write these numbers down and I'll be posting them in the worksheet. See you in class.